So we have already seen a few examples of matrix factorizations in a few of the past lectures, right? For example, the one on k-means, we saw that the k-means was a special case of a matrix factorization. So which are like problems of this form that you can formulate your problem as finding two matrices or learning these two matrices such that they minimize some function. So it's this kind of optimization problem. That's a matrix factorization, and we also saw that k-means is one of them. Then we also saw that not the GANs, but actually the principal component analysis was another example of this. So we also saw that can be seen as a matrix factorization. That was at the very end last week. I'll not go into details, but today we want to have a bit of general view on this and also discuss the case of recommender systems, which are maybe the most prominent case of matrix factorizations, and then on Thursday about text. So learning embeddings for text representation learning. So the motivation is from recommender systems for today. And there, I guess you might have heard of it already. It's a very natural setup. For example, you have D movies, and you have n users, and you want to ask or you want to study their preferences if they like some of these items or movies. Can also be products or anything, and what you want to learn from. So the data you're trying to leverage is going to be some preference data that users have given already. So this entry here means that this user small d has given 4 stars to the movie. This movie D has received 4 stars from user small n, for example. So yeah, movie 2, user 3. At that position, I have a rating of 4. So you can say that this is kind of a three tuple of like movies, user, and the rating. So this is the type of data you have, and what you also is interesting is that most of the data is actually not available. So this is unobserved. All the gray areas are unknown. So there's a lot of unknown entries in our problem, and the task here is to actually predict this unknown data. So that's what we're going to do today, and we will see that maybe one of the most natural ways to do it is going to be via matrix factorizations. So I hope the setup kind of makes sense. And also again about the data availability, you would say that maybe most of these most of the gray entries are really unknown. So you want to predict it, right? So maybe 99. So the vast majority of all entries are unobserved. They're just not there. And those we want to predict. So to train a model that can fill in this matrix. So predict. That's the goal. And there are many ways to do it. And for example, the easiest thing you would do as a baseline is to just take like maybe the average rating that users give to that movie, and you could fill in those entries. That is one very easy baseline. And there are of course many other baselines. And so just be sure that these entries here are not 0 or something. They're unobserved, right? We have no idea what the value those entries is. And there's also some nice data sets around. Actually, the one you have in the project 2, if you want to work with this, we actually have some kind of related data set to this Netflix prize data set, which was a very popular competition about 10 years ago, where like thousands of participants tried to really do all the tweaks, and it was kind of the first famous data science competition when people really tried all the tricks to fill in this data as accurately as possible and really try all the engineering methods you can. And in that case, they had like 20,000 movies, which is by now there may be more movies on Netflix and also more users. I think back then it was like 500,000 users. And in that case, really only almost nothing of the matrix is observed. And also this matrix would be extremely hard to store. You don't want to store this matrix as a dense matrix. This is way too big. So you want to store this matrix as a sparse matrix with these entries that you know and not do anything about the ones you don't know. So, okay, this is the recommender system. And we explained already the data that we have. So what I explained here was the entry X. dn is what gives the rating given from this user n to the movie D. And maybe it goes from 1 to 5. Here it was like 4 stars. Okay, what can we do with this? Let's try to formulate a loss function so that we can train a model and also formulate a model. So what we want to do is we will try to again use this idea of using 2 small matrices and trying to use their product. And that's going to be our model. So just try to find a matrix W and Z, which are quite small. I mean, by small, that has to mean that they are narrow. And same for Z. So when you lie down Z by its transpose here, then maybe you want to find these matrices which have only k columns or so, a very small number of columns, like maybe 20 or 30 columns or so, and then this is D and this is N. So N was 500,000 and D 20,000. So these are very large dimensions, but the inner dimension is very small. So that's the idea. And then what it does, of course, yeah, you know what it happens when you multiply 2 matrices. So to get the entry X dn, which we were talking about, we just multiply the nth row, sorry, the dth row with the nth column of Z transpose. So that's the nth row of Z actually, and that's gonna be our approximation of our rating. So we hope that the rating that this movie got from user N, we hope that this is roughly the inner product. So W, Z transpose, the dn's entry, right? So you just try to approximate the whole X with this product of the 2 matrices. Does this make sense? Okay, so we have a model. So if you ask for prediction, you just take this inner product, right, of the dth row of W with this column of Z transpose, right? So that's this prediction, and it's very easy to evaluate. So these are just these are K vectors, right? So they're very small, and seems to be quite efficient to make a prediction. So if you have an unknown movie and unknown user, I mean, you haven't seen these 2 together, then this is how you're going to make the prediction. Just yeah, just multiply these 2 green rows of these matrices. Okay, we have the model, and what we still need is a loss function, and that's going to be your choice. Of course, you can use any loss function you like. So what we're going to do here is we will just define the loss entry-wise. So over this whole matrix here, so everywhere we'll define a loss, right? And we sum it up over all entries. And so the training loss would just be the loss of the observed entries. So this loss here takes our model, compares it with a true value. So this is the true value, right? X. So this you can think of the label or so. or through a rating, right? This is from 1 to 5 stars. So this is this 1 to 5, and then this is what your model predicts, which can be 3.5, or it can be any number. And here the simplest thing we did is we just took a squared loss. So, but you could also do a absolute value. Maybe actually there's a few recent works which try to do this with absolute value, which is actually a bit nicer because it's more robust. So that's also something you can try. But the general principle to keep in mind here is that what do I mean by matrix factorization, right? It's, as we said already, I just mean that we minimize some function. So the loss function depends on both matrices, right? But the property we have here is that our loss function, what we train, is really depends only on the product of the two. So W times Z. So anything for any F of this form, so that's what we say is a matrix factorization, right? When you train your model like this by minimizing W and Z, these two matrices of a loss function of this form. And of course, that's the case here. So here what's F is, it takes these predicted entries and compares them to the true rating, and it only does sum this up over the observed entries, observed pairs N and D. So these are the observed. Observed entries, and that's it. So we have a loss function, we have a model. Now you would just run gradient descent, and that's basically the story. But we will discuss a bit more now on algorithmically how to do this and how efficient it is. But make sure you got the model and the loss function from this structure. So model is just W times Z. And omega is the set of observed entries. So that's here. Is there any question on this? So the loss function looks quite simple, right? It's just squared, and this product here is also simple. So looks not so bad. And now one thing you can ask is this an easy problem to solve? You could ask if it's a convex problem. And maybe some of you already have a suspicion or so. Well, we mentioned it. Yes. Your question is if I also optimize different Ks or just a fixed K. No, K is fixed here, yes. So yes, so K is fixed, so that's the width of this. This you have to choose, that's how you define your model. It's a bit like having two linear layers in a neural network, right? And you also have to choose how many neurons. So it's the same thing here. Or like in K-means, you also have to fix the K. Yes, K is fixed, and I will come back to it in a minute. So if K is too large, it can also be a problem and so on. Yes? Yeah, the loss function here is only defined over the observed entries. I think that was your question. So by observed, I mean the ones where we have the stars, right? So this is kind of our training data. So this is why this is the training loss. And then you would also maybe have to organize a test set for you to maybe you have a separate set of ratings which you actually have, but you don't use them for training. So maybe this one, and this one. I remove them before training, and that's my test set. And then you can also use a different omega to be your test set if you want to do that, right? But here I only gave you the training loss, and that's enough to, well, yeah, to define the training. So evaluation is another question of such models. Cool, and then. Okay, this was maybe a bit abstract. So also there's a very intuitive thinking about what is happening here, right? What happens when we multiply this vector of movie D with the one of user N. So so it really means that for each user we learn a vector, right? That's the movie vector, and this is the user vector, which we learn. So actually, when they are learned, right, then you would think this this will actually, these values which are in here, which can be any number, positive, negative, anything, but they should express the preference of you as a user, right? So maybe this aspect, you have a preference. So if it's positive, then means that you like this aspect of movies. So you have a large number here, and the movie maybe has also a positive number there, then it means that you like this type of movie. And also for the movies, they're just features, right? These numbers we learn, so they're learned features describing the movie, such that when we pair this movie with a user, we just use the inner product and we get a match score, right? How well our model thinks they work together, and that's just inner product. So it's very simple, beautiful model. And yeah, so this be called a user matrix. The movie vectors are the rows of W, and the user vectors are the rows of Z. So okay, we're just naming, nothing special here. So far so good, but now there's a few problems which come up, and there's namely two main problems. Like problem one, it's not a convex problem. So and why is this not convex? So it's not convex. We have seen this a few times. There's several ways to convince you that this is not a convex function, and we have seen a few similar functions which were also not convex. So one easy example is if you just imagine W and Z. So if your f of W and Z let's define it just to be W times Z. And in the simplest case is when these matrices are so small that they're just numbers, right? So the Z matrix has one number, it's a 1-by-1 matrix. The W matrix is a 1-by-1 matrix. So then what I have here is, this is a special example of a function f. It's not exactly the one we have here, right? Because we subtract something, but it's a function which is quite similar. So when we just take the product of two numbers, and I'm sure you have seen how a plot looks like when you do this. It's really this simple saddle function, W and Z, which happens to be positive here, of course, but negative here. And so far so good. Why is this not convex? Can anyone tell me? There's different ways to show that it's not convex. You just have to find, maybe you can find a counterexample, any definition of convexity, you can use it, and then you can see that maybe you can show that it does not satisfy this definition. So yeah, one easy case is, for example, when you look at point here and here, you can see that the value here in the middle is much higher than the value at the two endpoints. So this is a proof that this is a non-convex function. So along this red line, right, the function looks a bit like this. So it's a non-convex function. So you found a counterexample. It's non-convex. And yeah, I mean, the function x times y actually looks quite nice. You type x times y into Google. So then you see how this looks like. And of course, we have a bit more high-dimensional problem, but already in the one-dimensional case. So each of the two variables is one-dimensional. It looks like this. So it's this kind of saddle function. Okay, but we don't really have this function. We have actually a different function. So I'm not sure you're convinced yet, right? Because what we have here is, I just showed this example, if the loss would be W times Z, but it's not, right? It's a constant minus W times Z and then squared. So I ignored this. So that's why I was just showing you this very simplified model here. So maybe you would ask also if the other function, if you subtract from a true rating, so 3 stars minus the model, and then you square it. Now what about this function? Is this still going to be convex or not? And it's not, right? So basically, when you already have an element here which is non-convex, then the war is already lost, because then it's quite unlikely that by simple additional stuff, by adding a value to it or by squaring it, you're not going to solve the problem. Let's see, here is the example. If I take just a one-dimensional example with 3 minus x times y. So this would be, you have a ranking 3 stars, your model says x times y, and then it's squared, right? So here you can see what happens if we also do the square. And then this is how this would look like. So very nice function, and it's all curved to the top, so it looks kind of nice. It almost looks a bit like a convex function, but again, I would ask you, do you see somewhere where you could show that this is maybe not convex, or which kind of 2 points would show you a problem here, or would you say that this is a convex function? So any thoughts? So the gray plane on the bottom is x and y, right? And the vertical axis is the value of this function. So yeah, it's also non-convex, because, for example, if you take 2 points which are on the side in one of these sides, so for example, here you would see that between here and here you can put a line, and the function actually happens to be still above the line when you are in the middle, so that contradicts the line definition of convexity. So this is also not a convex function. And then when you do this with much larger matrices, x and y, or we call them w and z actually, then the problem remains. So this is still a non-convex function, but it's actually a nice function. It's almost a bit similar to a convex one, and there were some recent research works. Some of it even got a best paper award at NeurIPS, I think, to show that problems like this, matrix exercises like this, they don't have local minima. They don't have strict local minima. So for example, this function here is, I think it's a star convex, which means if you go to the optimum and you only take lines from there to somewhere else, then on any such line, it's kind of okay, right? But the line which I took, which was between 2 bad points, that was not okay. But I think it has the property that if you look from 0, 0, any line from there should, along that, it should be convex. That's not enough to make sure gradient descent finds the true optimum. But it's, with some additional theory, you can actually show that on such functions, sometimes the algorithms work fine. And also, in particular, you can show that there's no bad local minima. So from any local minimum here is connected to the global one. There's maybe many global ones, but they're all connected, and things are nice. If you find one of them, you're good. So this is a very interesting class of problems. It's surprisingly complex, right? For such a simple function, it has quite a rich structure, and still a topic of open research, actually. All right, so it's not convex, but again, that does not scare us so much, because we will anyway still apply our standard algorithms, which you're going to see in a minute, to use still gradient-based methods to iteratively optimize this W and Z. So that's what we're going to do next. Just a very small remark is the second aspect of identifiability. So it's also not unique. So it means, what I mean by not identifiable means that there might be several optima. Not a unique optimum. Why is that? So what if I give you one optimum, W and Z? Can you give me a different point, a different pair of matrices which are still optimal? Any ideas? Yeah. We could swap the places only if they're of the same dimension. Then you're right. Yes. So if n is equal to d, then yes. There is another thing you can do also if n and d are different. So, but we are on the right track. Yeah, you're saying I would multiply one and the other I would multiply with the inverse. Or did you mean to change the sign of one of them and change the sign of the other one? Yes. Both is true and works well, right? Yeah, if someone gives you this solution, then also minus is also solution. That's one trick you can very easily do. It's not very useful, right? But it tells you that yes, there's no unique optimum. And a bit more generally, you can take any scalar, right? Any beta times W. And then you just multiply the Z by the inverse of this scalar number, 1 over beta. So this is also optimal. Okay, so there are many optima, and again, it's interesting, but not necessarily a big problem, but it's good to be aware that this can happen. Okay, so that was about the main math part about the matrix factorizations. And yeah, it's quite an important concept, right? Because what we did here is more general, right? It's not only for recommender system, because what we did is kind of applying to any structure like this, any function f of a product of matrices. So that's nice. So this you can also use what we discussed here. You can also use it for example, what we saw for k-means or PCA or the word embeddings, which you're going to see on Thursday. So many applications. So, but then for recommender systems, again, the question will come up how to choose k. I think one of you already asked me. So, and again, it's unfortunate that I don't have a perfect answer. It's tricky. It depends. Depends if you. It's again going to be a trade-off. So if you set k extremely large, then it can be very easy to overfit, right? So if large k, I mean, if you set k bigger than n and d, well, which one? Maybe both of them. So if k is sufficiently big, then then you can just set W to 1 identity and set Z to X. And I mean, 1 times X is a perfectly fine factorization, and this is perfect. So the product is perfectly equal to X. You have 0 error, perfect training error, but it's maybe a bit meaningless. And of course, you can also do the opposite. So if the k is too large, then you will easily have 0 training error, which means perfect prediction on all these entries. But that's not the only useful thing, right? So you will overfit. You will actually not be meaningful anymore, right? Because the point is the point is not only to fit the observed entries, right? The point is to have a model which can, on one hand, fit, but on the other hand, also predict the ones we don't know, right? For that, you maybe have a small test set on the side that you can check this ability on a test set. So we can have this trade-off as usual between training error and then generalization. Are we also doing well on the test set? So are we overfitting on the train, or are we doing a good job? And so if K is too large, we overfit. If K is too small, we underfit. So, I mean, yeah, if you choose just K equal 1, you will underfit. And so here is actually an example with K equal 2. So that's still, that's not too bad. And what it's doing here is it's showing actually this movie matrix. So the matrix W. And so this is the matrix. And then what I'm showing here is just this one entry, whatever, Braveheart is one movie, and that has now 2 entries, right? It's so K equal 2. So this W matrix has only 2 columns, and then row D happens to be my movie vector, and I'm showing you the position of this movie vector. It's here, and then you can position all the movies you have after you've done the training and see what happens. So is this going to be an interesting embedding of movies? And actually, it works quite well. So yeah, I don't know. I don't know if you know these movies, but the idea is that you get the similar movies are grouped together, so they have similar features. So again, these features are not handcrafted; they are learned features. So, which is kind of the nice thing. And the same on the right, you again get kind of interesting interesting features from this movie. So it's not so clear what is the interpretation of these 2 features, right? We can't say that the first movie, the first feature means this and that, right? It really is a feature we learned, right? It doesn't have full interpretability. We just know that we have learned 2 numbers, and if you take these 2 numbers of movie, take it with the 2 numbers of you as a user, then the inner product pretty well explains if you like the movie or not. And what has been done on the right figure is actually a slightly different factorization, because they have just used a PCA, I think, PCA of dimension 2 of the original matrix. That's also something you can do. But no, actually, I think they have done the same thing as we just described. So they learned the factorization here with the squared loss, and then obtained the embedding of these movies. And you can say that, yeah, many movies which are a bit similar do actually get grouped together. What's also interesting is this method knows nothing about the movies, right? The only thing it knows is how many stars you gave it. It's really, there's no side information here. No side information about the user, no side information about the movie. So, for example, the gender of the user would also maybe influence what movies you like, but that is not used here, right? The system is only directly learning from the stars which were given to this. Okay, and then, yeah, how to choose K? It's a bit like in K-means, we need to do a compromise. Here it's actually nicer. We can say here there is a best K, and the best K is the one which gives you the best test error, right? So if you separate your test set, then that's what you're gonna use to choose the K, or even better, you have a separate validation set just to find the K. And once you get the best quality predictions, then you go with that K. That's the idea here. Okay, so we discussed a bit underfitting and overfitting. So, okay, small would be underfitting. And I guess the other case was clear. So if you have overfitting, either you can reduce the K, or if you don't want to, then there's another thing you could do to just use regularizations. And if you again look at this, then we have these two parts here. So we have F of W and Z. And now what we did here is we added a regularizer. So again, for Frobenius norm, it's just entry-wise square norm. So we put the norm, square norm of the two matrices. We said we also want this norm to be not too large. And then we also need to actually talk about this trade-off parameters. So we need to choose how important is that for us. So if you regularize, you always have this trade-off parameter, and that's also the case here. So if you overfit, this is another opportunity you can do to actually limit how rich is your model class, to limit it to not overfit too much. So that then you just modify your loss function to be the sum of the original F plus the regularizer. So. Okay. Any question here? All right, then we should talk a bit how to optimize it. And so, as usual, it will be stochastic gradient descent. And so this will be pretty standard. There's no big surprise here. It's maybe quite interesting how expensive it is. So because we were saying, I mean, these matrices are gigantic, right? So it's really, it can be 1,000,000 by 1,000,000. So it's very important that if we talk about algorithms here, then hopefully we can do steps which are cheaper than doing something with the full matrix. So that's one goal we have. So let's see if that's the case when we do SGD. And for that, if you want to run SGD, we always need a sum structured objective. And so yes, we do have that. So maybe you would even normalize by 1 over number of observed entries to show that your objective function is an average, but it's just cosmetic. So you do have the freedom to normalize or not normalize in training because the solution is the same. Right? So we ask solution W and Z. Yes. Oh, yes. Mm-hmm. Oh, sorry. So regularization is positive. So I just draw the circle a bit in a peculiar fashion. So the regularization is positive. Yeah, it always should add an additional penalty. So these are both pluses. Yes. Thanks. That improved the sign. Yeah. Any other comment? Okay, so let's see if we can optimize this loss function with stochastic gradient descent. And so yeah, we do have this nice sum structure. So this actually, let's just give this the name FDN, right? So that's the contribution from movie T and user N. And they're in the training set. So just a name, right? So then what we have is that, of course, we have a lot of these functions, right? L is this entire sum of all of them. The average of all these functions, Fdn. And each of these functions depends on both matrices. So it's a bit it's interesting, right? So, I mean, what this says is it only asks like if this one user who gave 3-star to that one movie, if how well is this set, right? But yeah, it depends on the user matrix and the movie matrix. And they are in this set, of course, and summed up. So nothing special here. And of course, if you do a stochastic gradient step, then we will just take one of these fn's and so f, it's kind of a joint index here, right? D and n is a pair, so over all these pairs, and each of these is a function. So goes from these two matrices it takes, and it outputs the loss function, which is how far away. So yeah, here's the loss function. You pay the squared error to the true rating. All right, so to run stochastic gradient descent, what we do is we uniformly sample one of the observed entries, so random sampling. So it's kind of important to sample from this thing, right? And then, so now we have a user n movie D. Now we need to say what's the gradient of that small part. So I need to compute the gradient with respect to the whole parameter W and Z. So the gradient for W is something. The gradient for Z is also something of this small element. And so, yeah, and of course the W gradient is as big as W is, which is D by K. And then this one, the Z one was N by K. Okay, so let's see if you can compute them. And that is, it's not so hard, right? You have the square, so you will do chain rule and so on. And we will see that we were able to take the gradient of this product here, right, of the inner product. So we will do that after the break, compute these two gradients. So we see this is a kind of a big matrix, and this is also a big matrix, which sounds a bit scary because we said we would rather have something very cheap, which does not depend on entire matrices. So after the break, we will see what information do we require to compute this one gradient, which is just for one entry, right? Just the gradient of this thing, 4 stars minus your prediction. What is the gradient of this? And what information is needed to do it, and how complex is it to compute it? And we will see it's not so bad. And then I'll show you the formula after the break. So, okay, to come back a bit on this approach that we learn these two matrices, I'm sorry, maybe I created a little bit of confusion here, that there's these two approaches to actually learn the W matrix, right? That's what I advocated, right? That's how we formulated the optimization problem. We want to minimize some loss, finding the best possible W movie matrix and user matrix. So we wanted to find the best features and learn them completely from scratch without any side information. So that's the minimization, that's the optimization approach. But then there is also the approach actually in the left picture is that these features were simply hard coded, right? So I should have been more clear about that. So if you hard code the movie features, so for example, if the lead actor is male or female, then you just put a 1 or -1, then that's why that's one approach you can do as well too. If you use expert information about users of movies, then you can do this by hand. But the cool thing is really to learn it, right? And that's what we do here. And we also see that the learned approaches have a much better generalization, right? Because if you just handcraft something, then you will always forget some dimensions, some aspects which are not straightforward, not completely obvious. So this is kind of on the left, it's kind of not ML, and on the right is kind of the ML approach, right? So we are on this side. So when we define either an optimization problem and we solve it using the tools we have, gradient-based methods, and that's going to be our next job, to discuss a bit what algorithms are available to find the best W, to find the best Z. And it's quite straightforward. The only not trivial thing is to actually compute these gradients, right? To compute the gradient of this one part of the sum or of the user matrix respectively. So how are we doing this? So I first want to do it for the gradient with respect to the movie matrix W. And then later I will show you for the user matrix Z. So for the W, we want to, so we have just one function, so of which we have observed the rating. And now of this one function, we want to compute the gradient of this dn, right? So you have fixed one particular user movie, but now you ask about the entire gradient of W of this thing, right? So it's a bit confusing with the indices here, so that's why I want to be a bit careful that, so dn is fixed now because we have, it was here actually, so we have decided what dn we want to compute the gradient of, and for now it's forever fixed. So why I'm making such a big fuss about this is because the gradient itself is actually still an entire matrix, right? Even if dn is just one entry, the whole gradient with respect to W is a matrix. So even if you just ask about the fixed f dn. So we need to ask about all entries of this W matrix, and that's the work we have to do. So all entries of W, so again, I have to give them some names, right? So W is a D by K matrix. So what I can do is I can ask about the something D K's entry, but D is already used, right? We said D is fixed. So that's why I need to say here, I introduce this other variable D prime, just to give names to the entries of W. So once I've given them some names, I can ask, so now just for one parameter, the D prime K, for this one parameter, how quickly is my loss function changing in this one parameter? And that's really what we're going to compute now. So now it's very simplified, right? The loss function, which of course is a number, the gradient entry we're asking about, which is a D prime K, and then of this green loss function of one sampled observation. All right, does this make sense to have? So be careful. The green D is fixed and the yellow D prime is kind of variable. We're asking about all possible ones. Okay, now what is it? The result is already here, which is a bit giving it away. But what we have to do now is to see. So now we ask about the D prime K's entry of W, and that's, you can imagine where that is, right? It's somewhere in this matrix. There is a row. The row is D prime, right? And we're asking how is that row influencing this loss? And the answer is it does not influence it at all, except if you hit the row here being actually the one we ask about D. So I mean, any other row of W has no influence on the prediction for DN, right? DN was whatever, 4 stars. We ask about this particular prediction, and that prediction, you know what the model is, right? It's the model tells you the D's row of W of the user is going to be it's going to be multiplied with the nth row of the user. But any other row of the movies has certainly no influence. So that's why if it's that's why I'm kind of explaining the outside stuff of this if yet, that I'm just telling you that if the rows are different, the one you ask about and the one we pre-selected, then there is no influence. But if you ask about d prime equal d, so for the row of W of that particular movie, the green movie, if they're the same, then there is a gradient. And then it's actually easy to see what the gradient is, right? So the row here gets multiplied and then it gets squared. So it's not rocket science to compute it. And Z for our purpose is fixed. So what happens is just that this row of W gets multiplied with the one of Z. And what is the gradient of this thing? It's actually well, I'm not asking of the gradient of the whole row, basically. I'm just asking about the gradient of d prime and a particular fixed k. Just this one particular parameter. So that parameter is somewhere. So this is row d prime, and this is the entry k. And this, so if I'm expanding what happens here. So what is happening is that, of course, this is this row of W and gets multiplied with the part of Z. And what it tells you is that the crucial part is the k, because this gets multiplied with the kth entry of Z. So, and that's what you have here. So here is the kth entry of Z. So that was the inner derivative, the derivative of W times Z. That is Z and K. So that's what you have here. And what is the outer derivative? Sorry, then it's squared. So the square disappears with the 1/2. And this here remains, right? So that's why you have this kind of prediction error remains. It's just not squared anymore. This is how much you're off, right? So this kind of prediction error. Well, not really error because it's not squared anymore, right? It's just the true value minus the predicted value. So true minus prediction. So this is a number, and then it gets multiplied with this red entry Z. So this is the gradient. And what's nice, this is very cheap to compute. So for example, so again, let's look a bit closer what's really happening. So X is the number of stars, so it's a discrete 1, 2, 3, 4, 5. So maybe this was 3 stars. And then this here is the model. So that's just the movie row multiplied with the user row, which is a very cheap inner product, right? This is extremely cheap. It's just because we ask only about the particular D and the particular N, right? So I just take the user row times the movie row, costs me K to compute this, and then I have to multiply with this number in the end. So this looks like a very cheap operation. So the movie row D and the user row N. Okay, this was one entry of the matrix. And well, yeah, the other ones are all 0, right? If you ask about the wrong row. And if you do this for all entries here, we have basically computed it already. We are done, right? So actually, what this is telling you is that this gradient here, it's actually, it's just one row. So the gradient has, so this is the gradient, it's 0 everywhere, right? It's area 0 except at this particular row. Which row was this? the row D. And then of course it's for any K you want. Okay, so this gradient matrix is very nice. We don't even need to store the whole thing. We only need to store the one row, which it is. And to compute it takes very cheap. So the cost to compute it is, I need to compute the prediction, which is costs K. So inner product of two K vectors. And then, so then this prediction is always the same. And then this one I have to do with for every K, right? For every K, the user vector has a different entry. And I will multiply it with the true minus prediction. So the cost is really, it's like 2 times K. So, or yeah, 1 multiplication, K multiplications and K additions. So really cheap. So I will just write order of K. So that's cheap to compute the gradient because again, N and D are huge. So it can be millions. But K is like 20 or 30. In the Netflix price, they got best results with like K equals 30. So quite a small number compared to the 500,000 users. So at a very cheap cost, you can compute a stochastic gradient. And that's all we need. When we have the gradient, we can perform a step. So then you would perform this step to change your W. And by changing it, of course, you would add a small value times the negative gradient. So as usual when you do a gradient step. So that was gradient of W, and gradient of Z is exactly the same story. Again, it will only be non-zero for the particular row that corresponds to you as user N. So every other users have 0 contribution to the prediction of this N, right? Therefore, they don't appear in the gradient, so we don't need to store it. So so same for the user matrix. So Z is user matrix, W is the movie matrix or item matrix, because of course this is not restricted to movies. This is recommender systems are used for any applications, whether, for example, also in ad placements, if they want to place advertisements in your browser, then they would also be, you could also use this approach to learn a feature vector for each advertisement and learn a feature vector for each user. And then sometimes it's also combined with side information. But here there is no information about user or movies. We just learn the factorization. So if you want side information, that's also interesting. So what you could do then, or maybe I'll come back later to this, is that, so here everything is learned, right? W and Z. But if you also have some additional knowledge that you want to use that about these users, I have some additional info, then I could just concatenate this hard-coded stuff about each user. So whatever knowledge you have about these users, you could add it on the bottom, and then you could, and here you would then learn additional parts which go together with this hard-coded information when the product of the two matrices is built. And then you would also add a bit hard-coded information about the movies if you have, and that could be together with a learned part of the user. So I'm just saying this would be a nice way to combine existing, this is called side information about users or movies. Can you also use that together with these learned features? So, and yes, this is also possible. Okay. But yeah, we are happy we can run stochastic gradient descent. It's very cheap per step. We have to run a lot of steps of this. So you just go through your data set. So that's you will actually have in the exercise. You will, I mean, here we said we randomly sample one entry, right? A user movie pair, we sample it, and then the next one. In practice, people just take a random permutation of this whole observed training set and then go through it. The same as you do with a SGD in the classifier or regression. So you just you go through all training examples once, so that's one epoch. And then again, you continue as much as you like until you are happy with your test accuracy, for example. Okay, the cool thing about this is that it's so cheap, and that this is quite exceptional that we can do a step which is way cheaper than any matrix operation, right? Because this is a matrix problem, but to perform a step, we only needed the vector operation. So it's extremely cheap. So that's not, it was not the case for other approaches we discussed so far. So even in k-means, right? One iteration is so everybody needs to do something, everything changes. But here we perform a step which is so cheap that it only affects one user and it only affects one movie, right? Because only this thing is gonna change of my parameters, because only this row has a non-zero gradient. So the movie matrix is kind of unchanged except the particular row that I currently look at from my movie D, which I've sampled. And same for the user, only the user vector currently active, which is N, only that one is actually changing in that particular step. And then you go to the next D and N. So yeah, you should run this because this is really 2 lines of code, and it's a beautiful algorithm, which is actually invented by, not by academia, but one of these hackers when there was this Netflix prize competition. Then they discovered this algorithm because it was so efficient to run. But back then, people didn't know how this, what function this algorithm is actually optimizing. But now we see that actually this is optimizing the average of these functions, so it can be seen as a case of stochastic gradient descent. So. But these methods were among the best performing in this Netflix prize, and are still used today whenever you have this kind of matrix factorization problem. So yeah, SGD, and there's also some variants of it. Maybe you could also try with Adam or so on, and maybe you can try with regularization if you want to get a better score in the challenge, or a different case, or maybe different loss functions. Like you could also use the absolute error, not the squared error. So these are all design choices that can be made to maybe try to empirically improve these predictions. So any questions on this? There was a lot of math on this slide. Good, so this was the iterative approach. Then there is a slightly different approach. So this approach is much more costly per iteration. And it also has a downside that this only works if you have like no missing entries. So, well, or at least only then it's like really justified. And this is just kind of an alternative approach, so to optimize, and it's kind of a bit less used, I would say. And what the idea is here is that you would just say you fix the entire W movie matrix, and then you ask what is the best Z matrix. So you kind of try to fully optimize for one of the two when the other is fixed. And that's something that we have also seen already, right? With k-means, that was also what was happening, even in a way, even with Gaussian mixture models, so EM, there was a bit the idea that one of the two parts is fixed and the other you can completely optimize. And yeah, sorry, this notation here, so it just means that this means all the numbers from 1 to D. This means all the numbers from 1 to N, and this is like cross product is like everything. So means now if omega are all the entries, then there will be actually a closed form solution to actually solve the thing when one of the parameters is fixed. So L of Z and W. When yeah, I just fix W and only optimize over Z. And yeah, what is this? It's just actually, it's just the Frobenius norm squared, right? So that's if everything is observed, that means the sum goes over all entries, and then it means that every entry is summed up of the the true entry minus the prediction, everything is summed up. So that means it's just the Frobenius norm, just the matrix squared norm of the observed, the true star entries and the predicted entries. So this is this special case, right? When you observe everything, then the problem looks like this, and it looks really simple, right? It's just asking which W and Z bring this smallest. So, and X are the true ratings. And if you approach it this way, where you just alternate, then this is kind of a coordinate descent kind of approach. So you just minimize the Z part and leave the W unaffected. So here you would just minimize Z and keep W fixed. So that is a case of coordinate descent, or to be completely honest, we call this a block coordinate descent, right? Because Z is one of the two blocks, or one of the two groups of variables that we have. There's millions of variables. I just alternate between perfectly optimizing Z and then perfectly optimizing the others. So this has a closed form solution. I mean, not the whole problem, but the problem of finding Z has a closed form solution. And how do you get it? You just set the gradient to 0. So, and if you do this, it's not so hard to check that well, here it's already the solution, but if you do this, then you get this equation, which means so there's a matrix inverse here, which looks scary, right? So this you would take to the other side. Then you would kind of have the equation something equals 0. So that was this gradient equation. You need to believe me for a second that this is what you get. So there will be an inverse of this matrix here. And to be honest, here we only do this when we have a regularizer, because this is exactly, it's the same thing as in ridge regression. So we will only solve the regularized problem, because then we will always have a unique solution for Z and W. So I will solve the regularized one. There is regularizer W and regularizer of Z. So I modified my objective. Sorry for not having said that earlier. And if I modify my objective, the same as in ridge regression, when we did simple regression from something to a target, this is kind of the same thing, right? Because if W is fixed, it's like a regression problem, right? It's just asking what are the best Z variables. And so what happens why is this regression, right? Because you see, Z is your variable. And so you can think of it as a vector or whatever you like. It gets multiplied with some features which are fixed. The Z is fixed. Sorry, W is fixed. So these are the kind of features which get multiplied with your variables. And then you hope that the features with your parameters together will approximate the truth here. So that's exactly like in regression. So if one of them is fixed, you kind of have a regression problem. And it actually happens to be a very easy regression problem. If you regularize it, then you can solve it the same way as ridge regression. So you have lambda times the squared norm you add as a regularizer, and then you set the gradient to 0. So this includes the regularizer. And then you get this kind of same formula as in ridge regression. So you get this kind of pseudo inverse, and then times the features, and the features here are depending on W, but also on the the true ratings X. So I didn't give the full derivation, but if you have a minute, that's easy to do. It can be a good exercise to play with a matrix derivative. So what is the matrix derivative of this simple expression? Two matrices multiplied and then squared norm. So okay, so this looks fine. So the good thing is it gives you the best solution for Z, for W fixed, and then you do the opposite. You go to the best W solution with Z fixed. So it's kind of this alternating algorithm. It's a bit expensive. So because inverse, of course, is expensive. So this is in no way as cheap as before, right? Before we paid K to perform a step, but here we have to take an inverse of a matrix, which is already, and not of a K by K sized one, but of a D by D sized one or N by N. Oh, wait a second. No, it is actually a K by K sized matrix. So that's that I will leave as a little exercise for you to figure out that this really is the gradient of 0 and the gradient of this part equal to 0. That this is how you get this formula. That's one thing for the exercise, and the other thing is to be clear about the sizes of these matrices, because yeah, actually it turns out this whole thing is a K by K matrix. It's quite small, but then to compute W with itself, that's quite expensive. So the result is K by K, yes, but still to compute it, you need to spend a lot of work. So actually, what is W? It's D by K. So computing this takes at least order D times K. So it's much more work than a SGD step. So okay, this is alternating least squares, and the other downside is it only works if we have all the entries observed, which is not really realistic. But the nice thing is we have a closed form solution, at least to alternate between the two steps. And then you still have to alternate many times, right? You cannot just do this once for Z and once for W, but you need to alternate lots of times. Yes, so that's this. And yeah, if you want to actually make this useful, then you need to do the same thing with missing entries. So that's the last thing I want to discuss today, and I'll not give you the full derivations because it's a bit annoying to do. And again, it's actually performing less good than SGD in practice. So this is more for you as a conceptual learning that yes, you can still ask the question if you can still take this loss function. So here it's for the real case when some of the entries are observed and some are not. And then again, the loss function is always the same, right? But what we ask here is can we actually compute the gradient of W? So this, of course, we can. We did that already. So we compute the gradient, that it's the same gradient as here, right? Just for the entire W. So that was the entire W gradient. But now not only of one function. Now I'm asking about all the functions together. So it's the sum of all these guys together. So actually now I'm asking about gradient of F, not of just one entry. So now I'm asking of a full gradient, not a stochastic gradient. So this is but we have already done the harder work, right? We have computed the stochastic gradient, and if I sum them all up, then I would get the full gradient. So because L was the sum of all these guys. So yeah, of course I can compute it, but the question is then, can I set it to 0 and solve for W? And the same thing with the other one, the gradient with respect to the Z matrix, the user matrix. Compute it, set it to 0, and then solve for Z. And so yes, this can be done. And yeah, how do you compute them? As we said, you use the nice thing that L is just a sum over all the observed entries, right? T and N are in omega, they're observed. So the training set of this, I think we call them FND, right? So yes, FDN, right? You can see the whole L is the sum of all of them. So, and we have already computed the gradient of each element. So we actually, so here we already know the gradient. So gradient is known. So this is another thing that you can think a bit more if you want. If you want to know if you can solve it in closed form for Z and then solve it in closed form for W and alternate again and again. So okay, and still cost is not super trivial, so it's going to be more than a SGD. Okay, so we have seen a few algorithms, the good one, and then two a bit more mathematically principled ones, which are more expensive, but also hopefully give you more progress per step, like the alternating, like in coordinate descent. So, which is very much in the spirit of what we have seen with other methods, so even with the Gaussian mixture models or the k-means and so on. So these algorithms are more of this type with the alternating. And then the SGD is more like the standard approach, as you would also use in deep learning and so on. And the nice thing here is like even memory requirement and compute cost per step are extremely low. So I don't need to store these gradients at all. They are just objects of size k basically, because everything else is 0. So very cheap per step and 2 lines to code. So this is something you can try in the exercise this week. And then why I'm also taking so much time on this one is because it's also going to be useful for word vectors, word2vec, which we're going to actually discuss on Thursday this week, which is we can actually use the same algorithm there. So here what we did here is we learned representations of users and movies. So these green vectors here, right? This is kind of the representation we learned for that particular movie. And this is the representation learned for the user, right? The vector we learned. And so you can also think about this as a representation learning task. So, and we will see that this same thing can also lead to how you can learn a representation of a vector. So a word vector, you can also do a similar thing to learn a word vector for each word. And again, there we have to think about what is going to be the loss function and so on. And it is going to be a nice unsupervised loss function. Whereas here it's a bit questionable if this is an unsupervised problem or not, because we still did use the ratings. So, but mathematically a nice approach which goes a bit beyond the standard regression models. But then also here you saw that it actually recovers kind of regression is kind of a special case of this, right? So if one of them is fixed, fitting the other is kind of like a regression problem. All right, I guess that's it for today. I leave you a bit more time for the project. See you on Thursday.